Hey everybody, this is Brad Dyke saying hi, reaching out to you. And today we're talking about the concepts and functionalities of the ability of using technology in the next step. So, what I'm referring to is simple. This refers to something that is finally starting to happen. I wanted it to happen about 15 years ago, but unfortunately, due to some controlling interests in the industry, to try to generate their own necessary capital and profitability, kind of stifled it a little bit. But with some key things that are just beginning to happen and are starting to take effect, in the next 5 to 10 years, you're really going to see a true change into the nature of our industry. So what do I mean by that? Well, coming from the world of AMDALLs and mainframes and then the world of x86 based platforms and into the world we know today of multi-environmenting those x86 environments into more advanced variations such as ARM environments, such as variance processing, clustering processing, and so on, the common denominator always comes back to the three rules of thumb. 1, processing power. 2, RAM resource. And 3, storage capacity. Bandwidth will always be somewhat necessary, but always on a limited capacity because you don't necessarily have to go beyond the system itself to get a result, i.e., such as a HCP, a supercalculator style strategy, where all it has to do is be local. So, what does this really refer to? Well, let me tell you. We've been working in an industry where we have what's called an integrated chip that has onboard memory and an I/O bus for communication. And the I/O bus has the ability of providing pathway to resources, or in this particular very simplistic device, which we have here, it can actually be localized with local resources, i.e. storage. So the whole thing about such a device like this is it follows a classic model. Now, what do I mean by a classic model? Well, the truth of the matter is the classic model is processing with its resources, a layer of memory or a buffer, if you want to call it that, and then, of course, beyond that would be capacity. Now, that just sounds like a motherboard, right? So let's look at a motherboard real quick. So with the motherboard, here you have your socket for your processor. Here you have your memory for your capacity, temporary random access memory, DIMM in this case. And then, of course, you have your I/O bus, which would reside where your storage capacity would be, which in this case would be the M2 sockets here. And this is a classical model of what I'm referring to. Now, believe it or not, this, yep, you see it? This is a remote, right? This remote has a processor, has a tiny bit of memory, and it has the CPROM storage capacity for its requirements. It has the ability of being basically the same thing as a motherboard itself. That's not all. Yep, you got it. Same model. Basically, in a nutshell, these technology environments follow the same model. Resources for compute, resources for rapid memory capacity, and somewhere, some way, a capacity to store static information, right? So, what's changing? What is finally starting to happen? This is important. Now, you see, in the world of a GPU, as you can see here, a GPU is basically a high compression of all the things we talked about. And it was actually NVIDIA and AMD that actually brought this technology to bear, and they began the nature of what's called stacking. That's three-dimensional computing processing stacking. They are putting chips on top of chips on top of chips. And by doing that, they could bring localized resources right to the die of the processor. Now, to me, that's a little bit of a flaw, but it's going in the right direction. And there's a lot of issues out there with that technology, but it does perform better than what we call the classical CPU-based RAM and storage model, which means a whole new introduction of technology that can be sold in the industry. Now, on top of that detail, SRAM, or SRAM style RAM, is a type of RAM that is also coming and is being finalized now, and you can defer to different manufacturers. I think it's SEAM and AMD and a couple of other companies that are developing the SRAM strategy, and that is to create what's called a tiering structure. So what does that mean? Now, a couple of years ago, I explained to you, what if a CPU, the die of a CPU, matter of fact, let me give you an example real quick. So, a long time ago, these guys existed. And as you can see, this is an Intel Pentium 6. And Intel was onto something, but they couldn't quite figure it out. So inevitably, because of the high failure rates of producing these chips, they eventually transitioned to separating the dies. So what came after that was what known as a Pentium 2, which had the processor in the middle and separate dies a good half-inch away from the processor, unlike this guy, which was directly died into the surrounding chip itself, giving you a spectacular capacity. These chips were way ahead of their time. But they give you the rudimentary nature of this particular next step. And let me explain. If you can take, let's say, 20 terabytes of capacity, right? I'm not joking. 20 terabytes. And it's all L1 level caching. Imagine 20 terabytes sitting over here on the sideline of the chip. Processors are here. Memory is here. Now, L1 is the fastest, highest performing capacity, RAM-wise, in existence. It's fast, but it's not segmentable out into multi-bandwidths. It isn't as flexible as other types of RAM are. But what if you could design a mastery RAM repository that could systematically break itself down, slow itself down from L1 level to L2, L3, and then into DRAM level, and then into static capacity. All of the RAM capacity could be capacity. Mind you, it could all be basically, outside of the basics memory requirements to run the processor, all could be storage as far as you're concerned. So imagine 20 terabytes. So let's say you have a 12 stack hypercore platform, right? So you'd have we'd have 12 processors in here. It's 24 hyper threads that are out there. And you assign 16 gigs per each. That's nothing. That's a drop in the bucket. 128 gigs. A laudable out and in point for the processor pool to work with. Then you have yourself your L1, your L2 for performance requirements for the processors, which is still a drop in the bucket. You could give them 1 gig each if you wanted. No issues. And at that point stage, below that, the remaining amount of that RAM that's there is slowed down dramatically, logically wise. It could be as fast as L1, but it doesn't need to be. It needs to be slower to follow what we call the paradigm of the pyramid and give you capacity, but it's all here in the die. So what's the point, right? So this compared to this, quite a big difference. The end result would be the next logical step is what's called a distributed bus. So if you have this sitting on a small die set, let's say a micro ATX board or something like that, a very small motherboard, if it's even that, it could be just something very much like a Raspberry Pi board. And it has a distributed bus. Now, the distributed bus could go 4, 8, 12, or 16 individual PCIe buses. Now, the reason why it could do that is because the localized communication is dramatically improved. So therefore, your pipes can handle the segmentation out. So when you have external NAS devices, i.e. SAS, mini SAS, and so on, and they're running high performance SSD or M2 style storage capacities, then they actually can have controllers that can match up to the speed of the actual capacity itself. So now the key thing here is, basically, I hate to say it, as much as I love them with a passion, you have to get rid of the motherboard. The end result is, unfortunately, you will end up having a new industry standard that will be like this. And on the back of it will have a Pentium Pro core processor. So this would represent your busing right here, which I would suspect may have optical integration into it to further the IOPS capacity that what you're looking for. But like I said, having something like this size kind of die support fitter for the actual unit itself, and it's running on 12-volt loads at roughly a few amps, is all you need. So with that being said, it's a new step in the right direction. So what does this look like? I mean, does this mean we're going to get, the whole PC industry is going to get upside down, flipped inside out, and pushed out another direction? Yes. I hate to say it, but it is true. Now, it's been 30 plus years in my experience. So that kind of fits the paradigm. But that doesn't necessarily mean there isn't a place for all the technologies we use today. There is a paradigm effect of the old with the new, the transition, the legacy versus adaptive technology today. Now, the other crucial thing that has to happen here in support of such a strategy, and this is what will slow this down, considerably down, is the software. Now, many years ago, I told everybody out there that, you know what? High performance video cards are a joke. Why? Because nobody's written the software correctly to use them. Yeah, you do get performance improvement. Yes, you do. Because of changing the hardware specs of the unit. But we're throwing away good video cards, going up to the next version video card, because nobody ever wrote the software to fully take advantage of these cards. You see what I'm saying? So all those, cards out there that are really proficient and functional and capable have a new future. But let's talk about the video cards, for example. Is this applicable for video? Yes, it is. And this most likely will be finally the point and stage where we will have what is called a wireless style communication process between the GPU with all of its resources inside the die in a very small bus interface, which would be as such. And of course, this is your GPU. But this would just sit off the side of your main CPU bus, and so on and so on. Now, you could also, if you wanted to take the best of both worlds, go to a new generational chips called CU GPUs. CU GPUs are basically have a true CPU in them that does the functionality of CPUs, but because it's localized in the die, it's able to accomplish a lot of things much faster than the use of a motherboard and a GPU. With that being the case, again, you could pull out some of the storage capacity of your primary chip, and you could have a GPU in here with its memory resources, and so on and so on. And yeah, okay, you'll run with only 10 terabytes of capacity. That's terrible, isn't it? But lo and behold, rock and roll. Now, that leads us to another very important question, SMP. Symmetric mode processing. All x86-based platforms are serial-based platforms. In other words, they do things in sequential order. Think of it like a loop, right? It always goes around in a circle. Every processor fits on the loop, and from 0 to 20,000, your computer system oscillates on that loop. And it does it by speed, and we call that the gigahertz speed, right? GPUs will work in there inside the loop, in its smaller loop, doing its thing, same strategy. Now, with that being said, can those things be addressed, and what does that look like when really there isn't much there to oscillate? That's a great question. And it comes back to the question that I brought up first, and that is software. Writing platform environments for software is critical. So you have to have the people who can write the software to maximize the effect and have the cycles to be able to accomplish this capacity. Any piece of hardware out there that runs on very basic, very asymmetrical style processes is not going to perform well at all. You have to optimize it. You have to get it to a good place. And hence, that's why I say 5 to 10 years before this takes effect. By that time, I will be out of the industry. I will be retired and pushing, I don't know, cucumbers in a garden or something. But anyways, the point is, this is where I will begin to phase out of this industry. And hopefully, though, I've been able to give you guys a lot of insight in regards to the stepping stones which are happening here. Now, the most important thing comes back to some of those other things I talked to, and please check out the videos about them, such as common device protocols. Common device protocols means bringing everything into the overall quote-unquote USB world, the Universal Bus Interface, and allow the devices to bring their own resources to the picture so that they're available, but not just available to a single platform like a Pi, but all devices that are able to see it. Which means if you build what's called a load variance cluster, in other words, one that gets a workload, and it does your printing, and it does your workloading, and it does your processing, and it handles workloads, and it does faxing, it does all these things for you. Well, all those devices have to be visible to the cluster, which means more than one Raspberry Pi. And it becomes visible, it becomes accessible, and it can be used. So those are crucial details in the process. So these protocols all come back to this because they're the next generation of our standing environments. So with that being said, another common denominator is universal network protocoling. Now what that basically means is in time, just by the nature of how it works, the communication process of different protocols will become fewer and fewer and fewer over time. Now, this was attempted with techniques like iSCSI, InfiniBand, and so on to try to get to a inter-based multi-device communication form. Now, what does that mean? Well, when you have in your possession SAS, you're using a SAS protocol traveling over proprietary cables. If you have IDE, yes, this is old, I know, or EIDE, in this case, this is EIDE, you see this cable interface, and it's using a proprietary protocol. SCSI is another example of that, but SCSI had the right idea. It didn't care what you were, it just cared where you sat in the SCSI loop. So you could have 16 SCSI devices of any kind, and those devices would just sit on the loop and cycle through, like I said, at a certain speed to allow the devices to do what they do. Now, EIDE did that same thing with what we call tape drives, which could allow you to have a hard drive and a tape drive and an LS120 drive and a zip drive, anything that could use, the 40-pin out connectors. And all you had to do was have a couple of controllers to give yourself 4 or 8 or more EIDE cable sets that could allow you to plug up those interfaces. Now, we got smart. We broke them apart by putting tape drives on one controller and hard drives on another controller and CD-ROM drives on another controller, and we got the maximum bandwidth from each of them by segmenting the workloads. But this needs to happen strictly at the software protocol level from now on. So if you have a bus that's, let's say you're using an optical bus, right? And the optical bus has 10,000 frequency variations. In other words, you could have 5,000 read-write simultaneous processes because you could use 2 frequencies, one for read and one for write, in a communication loop, and you could do that 5,000 times. Well, that's a lot of devices to put into that fiber optic looping process, because the newer types of fiber optic interfaces, such as optical chips and so on, use frequency level emissions, not just generic light emissions, such as our older generational light LED and laser ID fiber optic GPIX platforms. But the whole point of it is, when you take your software to the next level to fully maximize the effect of the hardware, the one key thing we see in this industry today, which is imperative, finally, is as the hardware is coming out, the software is actually starting to catch up. So if they can keep that discipline in check, and there isn't an action of monopoly to try to control a specific technology, very much how EMC did with a lot of storage technologies, then you have real progression and real development into that next world of ours, which is an important detail because that's your future, not mine. So with that, this is a conceptual video discussion about what do we see coming, what it really will mean when we say we have a processor board, which is really cool, by the way. It's about time. I wish it had come earlier because I'd have enjoyed that era of technology. I've gone through 4 eras of technology myself, from the technically 6 eras if you count the 70s, 80s, 90s, 2000 and so on, as both a young person and as a professional in the industry. There's some really incredibly awesome stuff that is coming, and my only hopeful goal is 2 things. One, that we stick to the non-monopolization effect so that technology can truly evolve correctly with wisdom being used to manage it. And secondly, that these technologies are used to further our minds and our capacities, not our weapons or our need to deal with paranoid kind of defensive capacities. When that happens, things just kind of get messy. But this is Brad Dykes signing off with this conceptual discussion, and it also talked to hardware to a certain degree. But really want to make sure that you guys have a chance to get as much as you can behind your belt. And my next video is going to be talking about assist tools that are really great about working with electronics and motherboards and systems and so on like that. I'll let you go. God bless and take care.